Okay, so I'm obviously not in the building, but the video is oh, it's a little bit grainy today, so hopefully I can clean this up kind of for the rest of this week. But it shouldn't matter too much. I've got mostly some stuff I'm going to show you kind of in Excel and kind of walk you through it that way. So let's see. So there should be for this week up on Canvas. Go to Files. We've got and I'll rename them. They're just going to be linear regression, week 16 lectures. And then we're going to be looking at, probably I'll open this GPA data file, but I'll also be using this traffic data 1 file as well today. Just kind of show you a little bit of what we can do with linear regression. So we left off kind of last week talking about linear regression and kind of looking at the relationship between an X variable and a Y variable. Right? So we had this idea that what we wanted to try to do is kind of minimize the errors that we're making with our predictions. Okay? So let's see if this shows up all right. This is my idea. I cited it last time. All right, so we've got, we're trying to make these predictions, right? Based off of, we're going to end up getting kind of these coefficient estimates, both for the intercept, right? But then also for kind of the slope or the relationship between X and Y, right? So we can come up with these predictions, but the actual Y is going to have this error term, right? Any individual observation, right? We can come up with this prediction and it might be close to the actual Y, but it's going to be off a little bit because every individual has kind of their own error term associated with whatever we're looking at. So if this is income and the X variable is education, well then, Bill Gates is going to have a much different epsilon term than most people. Right? So we're kind of an error term. So what we're trying to do with Excel is come up with what are the estimates that give us this line of best fit through the data such that we've minimized all these errors that we're making or the difference between our predictions and the actual Y. Okay? So in order to do that, there's a lot of math that would go on behind. If we're minimizing the sum of the squared errors, we could take derivatives in respect to each one of these coefficients, right? So we have this formula that would represent the sum of the squared errors. We're trying to minimize this equation, so we take a derivative in respect to each one of these coefficients. And equations and unknowns, we could solve it. But it's a lot of work to do by hand, right? There's a kind of a solution. I even kind of put up this link. You can go look at a kind of nice mathematical solution to how we would solve for these coefficients. But because we're going to have tools like Excel at our fingertips, we're going to focus for this class not so much on the computation behind the scenes, but the actual kind of interpretation of the results. So the way we said that we interpret these results, or we interpret these coefficients or these slopes, is it's a 1 unit change in our X variable causes the predicted Y variable to go up or down by whatever that slope coefficient, whatever that B value is, right? But now we said if we don't just have one variable on the right-hand side, right, we've got several, right? We could look at an example like this where we've got multiple variables on that right-hand side. Now this is, say, I think this example, we have police force expenditures. So $1 more spent on our police force would cause the predicted crime rates to go up or down by whatever this beta 1, or we can kind of think about this as B1 is, holding everything else constant. So I think we ended the last class looking at this GPA data where sheet 1 is just going to be the raw data. Right? So we had all this information, right? We could run kind of a general linear regression just looking at what's the effect of being a student athlete on GPA. But we said we also could include as controls everything else that we have data on. So go to this all tab that I believe that was what we kind of did right at the end of class. This was, I included all of these variables on the right-hand side. Right? So now the interpretation of this athlete variable is, this is the effect of being a one unit increase in this variable, which our athlete variable was just a 1 or a 0. So going from a 0 to a 1, going from not being a student athlete to being a student athlete, the effect of that on our GPA would be about 0.13, holding everything else in this regression constant. So it's like saying the thought experiment is 2 people with the same SAT score, they got the same score in this verbal math test, both female or both male, both kind of same race, both same total number of credit hours, both went to the same size high school. I won't worry about this too much for today's discussion, but the SAT squared would be the same if they had the same SAT score. And then kind of the same high school rank, that was all the same for these two individuals, but one of them is a student athlete. The predicted change we would see in their GPA is about 0.13. So as we include more, we'll call them kind of control variables on that right-hand side, we're getting closer to what we would be able to interpret as a causal relationship. But we still have to remember, it still is just evidence of a correlation, because when we only included just that one variable of the student athlete, notice we found a negative correlation, right? Negative 0.28. But when we include all these additional controls, that correlation is now positive because we've been able to kind of compare more so apples to apples, right? The thought experiment was basically two individuals who look very similar in respect to all the other variables that we were able to include in our regression, except for this one was an athlete, one wasn't. Now, we still could be leaving out very important variables. Right? So part of the discussion that we're going to have here, right, I'll start here and kind of go back there, is, R, I don't know, I have of course here, but so we have R squared, right, which is going to be some measure of how much we've captured in our regression in terms of how much is left unexplained, okay? So the idea is this R squared tells us what percent of the variation in our dependent, or our Y, or our left-hand side variable, we were able to explain with the regression that we ran. Okay? So obviously, the closer we can get to 100%, the better, right? If we could explain 100% of the variation, right, then there's nothing left out there that we haven't accounted for. Now that's almost going to be impossible to do, but we can get close to that. Right? So as we explain more of the variation in that Y variable, right, with our kind of right-hand side, or our X, or our control variables, we know we're capturing more, or we're getting a better prediction of that Y variable. So we don't have to worry too much about this. I'm not going to make you compute this by hand. I'll even show you where in Excel it gives you the R squared when we run these regressions. But you can kind of think about here, since the R squared is how much of the Y variable we're explaining, we'll look at this numerator is, well, we know what the average Y variable is. We can observe, say we're looking at that GPA example, we can look at the actual GPA of the students in the data set. So our deviation of our predictions from that average, we're going to kind of look at all those, right? Add them up for every observation, the deviation squared, divided by the deviation of the actual Y value, not the predicted, from that average. So this denominator kind of captures, excuse the cat, this deviation kind of captures all the variation in Y, and the numerator captures how much our predictions, the variation from our predictions and the actual Y. So it's like how much we're explaining out of the entire variation. Right? So if we go look at that, oops, I did not mean to do that. And so if we go look at that GPA data, right, you'll notice we only included the athlete variable, right? And kind of the equation we had was we're explaining GPA with that athlete variable. Our R squared here was 0.008. So I kind of said R squared is the percent of the variation we're explaining, but R squared is kind of in decimal form, right? Or kind of represented as a probability, right? Or the proportion of what we're explaining. So 0.008, we could think of this as we're explaining 0.8% of the variation in GPA when we only have this athlete variable. Now, when we include all the other control variables, right? Well, to me, just intuitively, whether or not someone's a student athlete is probably less predictive of their GPA than maybe knowing their SAT score or kind of knowing the total number of credit hours they're taking. So if we look here, once we've included all these additional control variables, our R squared has risen to almost 30%, right? Or the proportion of the variation that we're explaining with this set of control variables, or X variables, or right-hand side variables, we're able to explain about 30%, right? A proportion of 0.3. Okay? So obviously, this is still leaving 70% of the variation in GPA unaccounted for, right? So, while some of these variables matter, there's a lot of other variables out there that we're still not capturing, right? 70% of the variation we're still not able to explain even having all of these control variables, okay? So that's a general idea. I mean, so looking at that R squared kind of tells us, how I don't say accurate, but kind of how accurate or how well our predictions are doing at predicting the actual GPA of an individual, okay? Now, just kind of another reminder, when we have this regression output, we also can think about, well, which of these variables maybe look like they kind of actually have a relationship with GPA. So this is where for each one of these variables that we've included, we can look at their p-values, right? And we always start out kind of thinking, so our null hypothesis, is going to be, is that slope coefficient B? We assume that it's equal to 0, right? So we're assuming that the relationship between GPA and each one of these variables is equal to 0. So for each one, if we can get a low enough p-value, we can reject this, right? So rejecting the null is saying, look, I found enough evidence that I can reject that there's no relationship between SAT scores and GPA. So I'm saying I found significant enough evidence that there is some relationship. So if we look at the p-values here, we could go through and for each variable say, could I reject this null hypothesis that there's no relationship? Well, this p-value is pretty small, so for the SAT score variable, I could reject the null, or there is a significant relationship between SAT scores and GPA. Same thing for the athlete variable, low enough kind of p-value. Well, now here for this verbal math test, I could reject it at, say, the 10% or 5% level because my alpha is 0.1 or 0.05. But at the 1% significance level, I would fail to reject this, right? The p-value would be greater than 0.01. And I could go through the rest of these kind of variables as well. Now, one thing to kind of make sure you do when you're looking at these, if I see something like here, 2.9 e to the negative 22, that means move the decimal point 22 places to the left. So this is essentially 0. Anytime in your regression output you see this e to the negative, this is essentially 0. Like you could almost think about, if it makes it easier for you once you see that, I can almost just put zeros in here, right? Because they're so close to 0. When we go to make rejection decisions, something that is 0 or very, very close to 0 is still going to be less than 0.01, 0.05, and 0.1, okay? So that's kind of just some kind of going back. I know we talked about a little bit about that before the break, but that's how we use this regression output to reject the null hypothesis for this coefficient or slope estimate for each one of these right-hand side variables. Kind of introduce the idea of this R squared as well today. Okay. All right, so let's go back. So now we want to think about, we have to remember that these coefficients still only represent correlations. Now, when we include additional control variables, we are getting closer to a causal relationship. But even in that GPA regression, we said there's 70% still left unaccounted for. So I think I brought up this idea that if we were to run this regression of crime on police force expenditures and unemployment, we may even find, even after controlling for the unemployment rate of a county or whatever kind of district we're looking at, that we still see a positive relationship between police force expenditures and crime. So why, the interpretation there would be if I spend $1 more on my police force, it increases crime? Well, I mean, if we haven't accounted for a lot of other things. I'm guessing if we had actual data on this, we ran the regression, we're gonna get a really low R squared because the average income in the area, maybe, excuse me, different employment services that are offered, just the employment opportunities. Yeah, we're capturing that somewhat with the unemployment rate, but if there's just not a lot of job opportunities kind of moving forward in the area, or kind of the industries in the area are dying, like we want to capture that as well. So you can even think about what we're really capturing here is the correlation between police force expenditures and crime, but also every other thing that's also correlated with these two variables, right, that we haven't included in the regression. So maybe a better example, I kind of like this a little bit more. Let's say we go back and we look at some of that birth weight data. So maybe I think, smoking while pregnant is really, not good for the child. And so I say, okay, here's the birth weight. I've got all these different births and the birth weight of the child. What's the relationship between whether the mother smoked or not during pregnancy? Right? So the smoking variable is just a 0 if they smoked during the pregnancy, 0 if they didn't smoke during the pregnancy, 1 if they did. So the interpretation of our coefficient, a 1 unit increase in this X variable, is just going from 0 to 1, not smoking to smoking while pregnant. And if I run this regression, it could be, I mean, I've actually looked at this, it actually ends up looking like, well, this is negative, right? It's not, if the mother smokes while pregnant, the birth rate of the child goes down. Now, that makes intuitive sense, but remember, this is just a correlation. We haven't accounted for a lot of other things. And if we have information on, say, the mother's education level or the mother's kind of income level, right, those things are highly correlated with birth weights, right? Having more money, having higher education, you just are more likely to be making healthy decisions for the child while pregnant. But those things are also correlated with lower incomes, and lower educations are also correlated with the mother being more likely to smoke during the pregnancy. So we're not only capturing just the effect of smoking while pregnant, we're capturing in this regression the effect of the mother smoking while pregnant, but also all the other things that that's correlated with. So we need to be really careful when we make these kind of causal relationships, right? Especially if we haven't accounted for a lot of the other, any other control variables here. I think I brought this one up also at the end of last class. If I look at autism rates on organic food sales, it's going to look like a perfect correlation, but it's not causal, right? Organic food sales aren't what's driving autism rates. It's likely that an increased attention to health, higher income levels, more people are likely to go to the doctor. We're able to identify autism more accurately, and we're also more conscious about the health, and we have more income. So organic food sales are also being kind of driven by these outside factors that we haven't kind of captured here. Right? So, we could go through, there is a formal kind of mathematical proof that if I run this regression, right, some Y variable and some X variable, if I don't include any other control variables, call it X2, maybe another variable that's important, when I get down here, my estimate, so this star is kind of my estimate that I'll get for the relationship between this X and Y variable, X1 and Y. So it'll include the actual relationship, but also the correlation, right, between the X variable I included in the regression and this important variable X2 that I left out. Right? So anytime we kind of look at these slope coefficients, we have to be cautious and remember if there's other important factors that we've left out that are correlated with our X and Y variable, like this X2 variable, our estimates aren't going to be really just capturing the true relationship. They'll be capturing the true relationship plus this additional component, right? And we say that if we've left out important variables, we're going to have a bias estimate. And this is kind of referred to as the omitted variable bias. We omitted certain variables, we didn't include them, and they were important, and so our estimates are going to be biased because of that, okay? And we looked, I think, last class, a really good example of this was that athlete, and then kind of once we include SAT score, we saw we flipped this estimate completely, okay? So here's kind of a reminder, if you haven't already, how we get that data analysis kind of tool pack into Excel. So I want to show you here. Well, I'll before we go to the Excel, I always thought this was a fun one, right? So, if we leave out this important variable, I was calling it X2 on that previous slide, we could call it Z. We're going to have bias estimates. So I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe, right? Because maybe it wasn't taking the class that led to this better understanding. Maybe it was other things that made it more likely I would take the class, but also other things that made it more likely I'd understand the difference. So I was, that was kind of a fun little, excuse me, cartoon thing. So I think I really want to show maybe the power that this linear regression has. Right? So all these things in mind, I want to show kind of the power that statements we could start to make. So I have this pretty big data set. I think it's like 22, let's go all the way down. 22,000 observations, right? So it's a lot of observations. I've got the month, it's a traffic stop data. So I have the month the stop occurred. Now I pulled out here only, let's see, result of the stop 7. So reason for stop. So these are only speeding, right? These are only traffic stops that occurred because the officer reported that they pulled the person over for speeding. Right? So we're kind of comparing more apples to apples. I've kind of made sure that we're not, some of the stops aren't for, possession of a firearm or something like that. So we've only, or, warrant out for the person. So we've got only speeding. We've got a lot of other information about the officer and the driver. So to kind of clean this up, one thing I want to show you is we'll add in that regression tool, and I'll show you some pitfalls that we might hit with it. Okay. So we hit this data, or sorry, I was going to show you how to add it. So I already have it on my computer, but if you go to File, Options, then there's this add-ins. Double click on the add-ins. Go down here to Manage, hit Go. See, I've got the analysis tool pack checked, so I want to make sure it's a check mark next to it. Now when I hit OK, it'll be here under that data tab. On a Mac, I think if you go, depends on kind of what year, but usually I think File Options on some, but sometimes I think it's under the Tools. There's like a Tools tab, and you can go to Add-ins, and it's kind of a similar thing. You can manage add-ins, and you click on the data analysis tool pack. If you're having any difficulties getting these added in, please reach out to me via email. I can kind of look up, let me know what type of computer you have or why you're having some, if you're having any issues getting that added in. Some of the older Macs, you might have to download this package called Stat Plus LE, I believe. But we can get that sorted out. Just try to do it early and contact me so we can get that ironed out here this week. So now that I go to my data tab, I go to data analysis. Now I've got all these options, right? So I want to do a regression. So I scroll down here to regression, hit OK. So my Y variable here, I've got all this information. I'm actually going to look at just whether or not, once this person was pulled over, whether or not they got a ticket. Okay. So my Y variable, I want to be this ticket variable. So Control Shift or Command Shift on a Mac, hit the down arrow. Here, my X variables, I'm going to scroll back up here to show you. So let's say I want to control for the driver's age, the officer's years of service, but maybe also whether or not the driver was male. So I go here, I click on driver male, hold control. Actually here, I'll select whether or not the driver is male. I'll then also try to include, so I hold control, the driver's age and years of service. So it looks like I've selected, these are my three X or my three right-hand side variables. Okay, so it shouldn't be a problem. I selected the labels at the top, so I'm gonna click this labels button. I'm gonna put it on a new worksheet, so I have this selected, it's kind of the default, and I'll hit OK. And it gives me this contiguous reference error, so I hit OK. All right, what went wrong? So I hit cancel, I'm gonna look at this. When I run a regression in Excel, if I want variables that in my data set aren't next to each other, Excel can't do that. So what I would say typically to do is, here's my kind of raw data. So I'll rename this sheet. Here's the original data, right? I'm just going to Control Shift, go over and down, excuse me. So I've selected all the data, copy it. I'm gonna paste it over here on a different sheet. And now, because I need those to be next to each other, I'm just gonna get rid of the variables that I didn't want, right? I don't want these race identifiers in this regression, so I get rid of those. Now, whether or not the driver's male, the driver's age, and the officer's years of service are all right next to each other. Okay? So now when I go to the data analysis, hit OK, I'm going to select this ticket variable as my Y variable. For the X variable, I want the driver, kind of gender, age, and officer years of service. And now that those variables are next to each other, now when I hit OK, now it can run that regression for me. So it's just the way that kind of Excel operates. It needs those variables to be next to each other. Okay. So now if we look at this output, we can start to interpret things. If we look at our R squared with these three variables, we're not explaining a ton of the variation whether or not someone gets a ticket, right? 0.01 is the proportion, so 1% approximately. We do have kind of the interpretation we can make of these different variables. So remember, it's always a 1 unit change in the X variable causes the predicted y variable to go up or down by whatever the coefficient is. So let's, for the sake of kind of reading, zoom in a little bit here, make it easier. So we'll start with officer's years of service. So 1 more year of service, right, predicts that the probability, right, that the officer writes a ticket. So the reason why, I can think about an increase in my y variable here. Well, the original y variable was what? Whether or not you got a ticket, so just a 1 or a 0. So changes in the y variable, changes in whether or not I got a ticket, are like moving closer towards that 1, right? So increases in the probability that I don't, that I do get a ticket relative to not, right? So my y variable here is just a 1, 0. So 1 unit change in my x variable, which was officer's years of service. So 1 more year of service, the predicted y variable, the predicted value of whether or not I get a ticket goes up by 0.001. Or, the probability I get a ticket goes up by, well, I should have said 0.001. It's actually, if we round it, 0.002 here. Right? Interpretation of driver's age. For every year the driver gets older, right, every additional year in age, the predicted value of whether or not I get a ticket goes down by about 0.004. And this kind of makes, maybe makes sense. The officers that are on the, serving longer, maybe are more likely to be I don't know, maybe not as less forgiving, while as the driver gets older, you're just less likely to get a ticket, right? I know that holds true for me. I just did a lot of dumb things when I was young driving, right? So now the other one that's a little bit interesting is kind of whether or not the driver is male here. So the prediction that we would make is, if this goes, a 1 unit change in this variable, well, this was a 0 if the driver was not male, 1 if they were. So a 1 unit change would be going from not being male to being male, or a male relative to kind of a female. The predicted change in whether or not they get a ticket when they get pulled over is about -0.009. So here we would say males are actually less likely to get a ticket if they're pulled over for speeding. Now we have to be careful because, right, that's a correlation. There's a lot of other things we haven't controlled for. And also, can we actually say that this is a significant effect? Remember, just like when we were looking at sample means, we were making decisions of whether or not we could reject or fail to reject the null. So just because we saw something different than the hypothesized true mean, if it wasn't different enough, right, and we didn't have a low enough p-value, we actually couldn't reject whatever we assumed to be true. So just as a kind of reminder, our null hypothesis here was that these slope coefficients are equal to 0. Well, if I look at that, was the driver kind of male variable, the p-value is 0.15. So at kind of our normal levels of significance, 1, 5, and 10%, alphas of 0.01, 0.05, and 0.1, my p-value isn't less than any of them. So I can't reject this null. So if I fail to reject the null here, what I'm saying is the true relationship between gender and whether or not someone gets a ticket when they're pulled over is actually 0. It could be, like, I didn't find enough evidence to where I could say that this isn't true, that there is no relationship. Now for these other two, here we've got one of these examples where we've got that e to the negative. So these are essentially p-values of 0. So we could say with 99% confidence, or at the 1% significance level, these are very significant, right? We can definitely reject that there's no relationship between age and driver's age and officer's years of service and whether or not someone gets a ticket, right? These estimates, we could say are very significant, right? We can reject the null at very high confidence levels, okay? Any questions for those of you who are on before I kind of keep moving? Okay. The other thing I wanted to do with this is kind of show, so let's go back to that raw data. So I've got officer years of service, driver's age, whether or not they got a ticket. I also have some race identifiers. So here I've got whether or not the officer is white, whether or not the driver is white, and then kind of with that combination, included this additional variable, which is the officer white and the driver non-white in this stop. So notice when the officer is white and the driver is non-white, this variable is a 1. All other times, it's a 0. Okay? So I'm going to also want to include, so I'm going to go here to my data analysis, regression, hit OK. So my y variable is still whether or not they got a ticket. So I'm going to select that variable. Now my x variables I want to include from driver being male, right, all the way over to officers either service. So I'm including all of these as my control variables. So if I'm including additional variables in my regression, right, I can probably imagine my R squared is going to go up. Right? I'm hopefully capturing, you know, if I'm controlling for more factors, I'm likely able to explain a larger amount of the variation in that Y variable. Well, I am here. It went up from like what, 0.01 to 0.03, but it's still relatively low. So when we make these interpretations, we're going to, you know, I'm going to make them, but remember in the back of your mind, you know, there's a lot that's left unaccounted for, okay? So let's look at these variables. So, you know, we already kind of made the interpretation in the previous regression of age and service, also whether or not the driver is male. Here, what's kind of interesting, and I think this was, if we're thinking about the setting here, I believe this is described as a large U.S. city in southeast Texas. I'm guessing this is Houston, right? So if we look at if the officer is white, right, they're actually much less likely to write a ticket, at least based off the data we found. And that p-value is pretty much 0, so we can say it's a pretty significant effect. Right? If the driver is kind of white, it's less likely that they receive a ticket. So maybe some evidence of some type of discrimination going on here, although the p-value is relatively high there, right? So we can't really say that the driver's kind of race alone has any impact on whether or not they get a ticket. Now here's where the really interesting result comes in. If we look at this kind of additional variable that, okay, but if the officer is white and the driver is non-white, right, what's the kind of additional effect, you know, if that's a situation, what's the change in the predicted Y variable of whether or not someone gets a ticket? So if we see there, we've got a pretty positive coefficient, right? You're what? The probability goes up by 0.06 almost. So if your officer is white and the driver is non-white, that driver is about 6% more likely to get a ticket than, you know, if the officer is white and the driver was also white. So and the p-value is pretty much 0, so we can definitely reject the null that there's no relationship. So this is kind of troubling, right? This is, you know, if I'm looking at this and I'm the you know, mayor of this town, or I, you know, even high up in the police, I say this shouldn't be happening, right? Now, you know, we haven't accounted for everything here, but you have to remember, like, the whole data set even started, there was, you know, all these are just speeding traffic stops. So, you know, we are missing a lot of it, but this still is troubling, right? Probably would want to go out and get more data, be able to control for more factors, and get more at this cause relationship. But even just that we see that there's a correlation here between kind of cross-race kind of discrimination, this is troubling, right? Now, I was somewhat interested in this, and I thought this was a unique data set. And I said, well, you know, that's really bad. Oh, mailman's here or something. So, hold on. Hey, I'll have to edit that in post. So now let's look at the Y variable. Instead of being whether or not they got a ticket, let's look at whether or not the person ended up getting arrested, right? So we'll select that variable as our Y variable and still include the other control variables, right? Everything else we had in the other regression. So we'll hit OK here. Now we have to remember we're looking at, oops, I want to go to view, not data. Now our Y variable, right, is whether or not someone got arrested, okay? So now when we're looking at interpreting these, right, it looks that, like now, so if I have 1 more year of service, the officer is less likely to make an arrest from just a normal speeding, you know, traffic stop pullover. Looks like when the driver is younger, they're still doing dumb things, and they're kind of, or sorry, actually no. Now if the driver is younger, they're actually less likely to kind of be arrested here as well. But what's interesting, if we look now at, is the officer white and the driver non-white variable? Well, it looks like you're still more likely, right, if you're a non-white driver and you're pulled over by a white officer, to get arrested from a traffic stop. However, our p-value is 0.39. We can't reject that there's no relationship now between this variable and whether or not you're getting arrested, the Y variable. So, you know, if we look at this, I guess it's somewhat maybe relieving. It's a relief to see that this kind of cross-race discrimination isn't happening, when it comes to being arrested, but it's still happening for receiving a ticket, which is, a terrible thing, right? We don't want discrimination going anywhere, but at least it's not, more likely that someone's getting arrested because of some type of racial discrimination. Okay. In fact, if we look at any of the race identifiers here, all the p-values are high, so there doesn't look like when it comes to getting arrested that there's any relationship between the race of the officer and the driver. But when we're looking at kind of whether or not they get a ticket, looked like there were some significant effects here and kind of some evidence of discrimination. So I think it is a good example that kind of shows you what types of questions we can start to answer with this linear regression. And it's pretty easy to do. Once we have that data, right, in Excel, right, that data analysis tool is going to do all the computation behind the scenes for us. And so then it's just left open to us to be able to interpret these, right? And it's always the same thing. A 1 unit increase in this X variable causes the change in the predicted Y variable to go up or down by whatever this coefficient is. Now, another thing I want to mention here as well, because I wasn't saying this, but anytime I make those interpretations, when I have other X variables, other right-hand side variables, other independent variables here, this was the additional, well, here we'll go back to this was the one for the ticket, right? So when I interpreted this as if the officer's white and the driver is non-white, the expected increase in whether or not I get a ticket is 0.05, holding everything else constant. So holding the driver's age constant, holding their gender, the officer's use of service, and if we were to include other holding everything else that we put in that regression constant, then that's even. So that's a little bit more powerful, right? Because now I'm comparing like two drivers of the same age, getting pulled over by an officer with the same years of service. They're both the same gender. But now in one case, the officer's white. Actually, both cases, the officers are white, but in one of them, the officer's white and the driver's non-white. What's the additional impact of that? So pretty powerful statements that we can make. Now, like I said, let's take these with a grain of salt. This is a fun example, and it lets me show you what kind of questions we can answer. But we have a very low R squared here. We're still, a lot of the variation, whether or not someone gets arrested or gets a ticket, is left unaccounted for. If we had things like prior arrest records or something for the drivers or something like that, those would probably increase the R squared quite a bit here. Okay. And this is kind of just an explanation of the variables that were in that data set. Okay. I might save this for Wednesday, and we'll do more. Yeah, I'll save that for Wednesday. So I might actually kind of end this a little bit early, kind of do a shorter kind of lecture here to start out the week. I think one thing I want to kind of mention is make sure you can get that data analysis onto your Excel. I'll get a final kind of Excel assignment posted today. It should be a lot easier than the other ones. And so if you've missed one or you didn't do well on one in the past, remember, I'm going to drop the lowest one. So if, I will say that I think this last one's quite a bit easier. And so if you've already, say, done the first three and you got a pretty good grade on it, well, that fourth one is supposed to be due this Friday. Well, this fifth and final one, I'll have set the due date of next Friday, right? And like I said, I would probably choose that one because I think it's a little bit easier. And you really only need to have 4 of the 5 Excel assignments done. So, because I dropped the lowest one. So if you don't do one, it drops to 0. Now, if you do all of them and, 4 of them you did, I don't know, let's say you got 4 90s and then 160, the 60 gets dropped. So it's kind of up to you. I know things are probably crazy kind of here moving towards the end of the semester. But I want you to keep that in mind because I dropped the lowest homework. You really only need to do 4 of the 5 Excel assignments. Now, if you only do 4 of the 5, right, and on one of those you did very poorly, well, that doesn't get dropped anymore, right, because the dropped one is the one that you didn't do. So kind of make your decisions accordingly. Also, I want to mention something here. I'm also going to post, I think I forgot to open it up, so I'll have to find it here for us. One thing I'm going to put up, it's going to be the same as, where's my figure out? Where is it? Search here. So figure out. see if I can get it. Here we go. So I'm going to post this little Excel file, right, up on Canvas, and you'll open it up and it looks like this, and you kind of can see we've got the different categories that are weighted for this class. So you've got your Excel grade, your kind of iClicker, and this is like your total grade for all, your average across all the Excel assignments, your average, iClicker grade. These should kind of be displayed to you on Canvas. We're going to, I don't want to show you the grade book here. So how can I do this? I can go to Home. I can go to Student View. And I can go to Grades. So you can kind of see, like, if I go down here, right, I can find my Connect grade. I can find my Learn Smart grade, my Excel assignment grade, Connect, all these kind of different, sorry, Connect grade is a little different. So Connect assignments had the original ones. So the ones in which we have kind of a way to assign to, you can find these right here. So you'll plug in whatever your Connect grade. So let's say on average, you get a 90 across the Connect assignments, 90 for iClickers, 80 Excel, 100 on Learn Smarts. You then put in your 2 exam scores. So maybe I got a 50 and then a 70, right? So so whatever your scores are, you would put in here, and then it kind of tells you your potential grade. Now, the one thing that we have left is the final, right? So I could start to play around with, well, if I got, let's say I tanked the final, right, I get a 25. If this was, all my other grade, I'd still be right below a 70. So if I get like a 26, no, maybe a 30. Okay, so all I have to do is get a 30 on the final, and I'd still get a C minus in the class. Or I say, well, what if I did really well in the final? Okay, if I get an 80 or get an 81, okay, what would push me up? Well, probably 83, I'm gonna guess. No, so 84. So I get an 84 in the final, I can still get a B in this class, right? And the reason why is because I have it set up so that it identifies, hey, geez, he's going crazy there. So it identifies your kind of highest, lowest, and middle exam score, and kind of, even if this was out of whack. So notice if I do like a 55 here, see, it orders them, kind of identifies them for me and shows me that potential grade. Okay. So I'll put that up on Canvas. You can kind of play around with that. If you have any questions on it, let me know. But that kind of gives you a good idea of where you're going to kind of end in the class based off of like how well you would perform in that final. Okay. Any other questions for me before we kind of get going here? So you have that current 4th Connect and Excel assignment due this Friday. I'm going to get the other kind of, I'll get the last Connect and Excel assignment posted today, and that'll be due next Friday. And like I said, those are probably easier assignments. And if you've already done the first 4 and you're happy with your grade and you don't do the 5th one, it would just get dropped, right? I'm dropping the lowest of each type of homework, okay? So if there's no more questions from me, we'll probably end it here. I'm not seeing anything in the chat. Okay. All right. I'll be on again on Wednesday and Friday at 11 o'clock, doing probably some more regression examples. And if you have any questions kind of over any homeworks, then I can almost use it kind of like office hours as well. Okay. All right. We'll see you guys on Wednesday.